Okay, so let's now pick up where we just left off. Hopefully you've had a chance to think over that great table. And so what we're going to talk about now is we're going to discuss that question a little bit. I'm going to give you, for this part of the video, some canned answers, so to speak, and hopefully that was supplemented by some discussion amongst us all after the end of the previous video. In any case, so I had previously shown this table here, which indicates a big old table. It was a little bit smaller in the previous slides. Which state has the highest income? Is there a relationship between income and education? And is this consistent everywhere? So those are the questions that I asked of this table. And to ask a question of a table like this is a little bit hard. One of the easier things to do here is to answer the first one, which state has the highest income. You can just roll your eyes across the table to look for the largest number. And keep in mind as keep the number in mind, the largest number that you've seen as you move your eyes down the list. However, when we plot, this thing here is called a scatter plot, and what we do in this scatter plot is for each state, we place the dot for the state along with its label at a location such that the X location is the per capita income with a range from 10,000 to the left to 19,000 on the right, and the vertical dimension is the percentage of people with a college degree, with 16% in the lower, at the bottom of the plot, and 35% at the top of the plot. And what you can see here is that indeed the state with the highest income has a plotted point farthest to the right because that's the highest value of per capita income, and the state there is in the upper right, and that's Connecticut. So there's the answer to question number one. It's Connecticut. The answer to the second question is a little bit harder to determine when you look at a table. And part of the reason for that is that the question is a very complex one. It requires for you to, in some sense, analyze the behavior of the collection. And a scatter plot is a great way to answer questions like, is there a relationship between two variables amongst a bunch of data cases, each data case, in this case, being the individual states in the data set? And so the answer to that is, generally speaking, yes to question two. There is a relationship. That is to say, broadly speaking, the higher the percentage of people with college degrees there are, the higher per capita income. And that line that I've drawn from the bottom left to the upper right is an indicator of the correlation line. That is to say, the quality of the correlation, the relationship between a percentage of folks with college degree and per capita income. Now, we already knew that in some sense from our own life experience. I would expect that many of you are right here in this classroom, virtually or really, because you know that when you have a college degree, the likelihood of a high-paying job is greater. And so the answer to question two is outlined in this green blob that I'm showing here, that yes, there is a correlation, and it's true for many, many of the states, but not exactly all of the states in this plot. The answer to the third question really depends on what your answer is to the second question. That is to say, if there is a strong correlation, and I would argue that in this plot there's a pretty good one, then the notion of exceptions has to be defined in relation to what the primary behavior is. The primary behavior in this case is a broad correlation, but there are exceptions, and those are circled in red here. Utah and North Dakota have higher levels of higher education, but not necessarily high per capita income, and Nevada has the opposite relationship of higher per capita income, but not necessarily a high level of folks with college degrees in that state. So that's an example of visual reasoning. Visual reasoning is something that you can do about all sorts of visualizations in data-driven pictures. And what I'd like to talk to you about now is fields of visualization that have been in use for the past 30, 40, 50 or more years. And there are broad categories of visualizations that we are interested in pursuing in this course, and some other categories that are just simply out of scope for us. And one of those categories of visualization is scientific visualization. That is, the visualization of data that has a built-in spatial component associated with some kind of real process or scientific process, say the bonding of molecules or the effect of fluid flow across the surface of something. And the data that you typically get for scientific visualization has a very strong structure, a very strong geometry and natural geometric structure associated with it, such as chemical data, wind flows, whatever you may have about some real process that you're interested either in measuring or in simulating or something like that. In IAT814, we acknowledge the existence of scientific visualization, but we're really focusing on visualizations where you're not handed a geographic object or geometric object to start with in order to construct your visualization. A related field to what we do is information visualization, and that is where visual metaphors for non-inherently spatial data are put into play. And information visualization is, in some sense, a predecessor field, a founding field for visual analytics. Typically, it's the people who work in this area are interested in abstract visualizations of abstracted data and interested in creating mappings from the abstract data of the data set to a geometric structure that you create in order to understand the data set. So typically what you do is you assign structure and position to information that doesn't have geometric information. And the transformation of the symbolic into the geometric is what you're doing in information visualization. And in the course, you will be doing a bit of that as you develop visualizations for problems. Another thing that's important about it is you typically find yourself finding an artificial memory, creating an artificial memory that best supports our natural means of perception. As I said in the previous lecture segment, one of the things you care about is trying to remember what's going on in your data, and it can be a little bit hard without memorizing it, and visual displays like this create that artificial memory for you and enable you to reason about more complex things, given that you've got the data visually displayed in front of you. Another related area that is partially geometric is spatial geovisualization, and here are a couple of examples of that. On the left is a map of a hurricane striking southern Louisiana. It is Hurricane Harvey, not the recent Hurricane Laura, but in some sense the information being conveyed there is of a similar kind to what you would have seen over the last few weeks in southern Louisiana. On the right is a plot of the southeastern United States. That's South Carolina on the far bottom right, North Carolina, Virginia, etc. And what is shown there is the various U.S. states and the individual counties, and the colors are assigned according to some value about some quantitative information about each of the counties that you see there in that map. So geospatial visualization has given to you two primary dimensions, which is the geographic substrate that you care about, over which typically there is some other information that you wish to plot. On the left, wind speed and rainfall density, and on the right, some other quantitative information that we haven't explicitly shown. So visual analytics is about bringing together all the aspects that we spoke of earlier. Visual analytics is the science of analytical reasoning facilitated by interactive visual interfaces. The fact that they're interactive is important to us and important to the field of visual analytics. If they're not interactive, it's not so useful and valuable as a tool. Visualization system is not so valuable as a tool to support the analytical process. Because when you're doing analysis, you typically don't want to stare just at a single display alone. You will want to interact with the data and refine your query, refine your question. As Daniel Keim says, quoted here, computers are incredibly fast, accurate, but stupid. And humans, by contrast, are slow, inaccurate, but brilliant. And together, they are powerful beyond imagination in creating analytical effects and enabling us to understand complex phenomena. So, following on that definition of visual analytics is there are a number of visual analytics workbenches. This is an example of one. This is called Inspire. This thing, its purpose is to do document analysis and visualization, as well as make links to other aspects of visualization. And in this display, you can see there's this cloud of dots here. The dots, each dot in the display, each dot is very, very small in this display. It corresponds to a document, and what has gone on is each of the documents in the data set that's being shown here has been clustered, so like documents with similar themes are located together. And you can see down below that there are a number of facets of those documents that are being presented in the document data set. So this is a visual document analysis system that is an example of a visual analytic workbench. So visual analytics, the idea behind visual analytics is to bring together the capabilities of the human on the right, human cognition, perception, visual intelligence, and decision-making theory, in collaboration with the machine's capabilities of doing statistical analysis, data mining, data management, and get the best of both sides, semantics-based approaches, information design, where you're really taking advantage of the human capabilities to be able to really drive what the machine is capable of doing with massive amounts of data. So now let's switch gears a little bit. We've talked about visual information and showed a number of examples. What I'd like you to do now is to just take a look at some handcrafted elements that have some common features to visual analytics, but you wouldn't necessarily see any of these as the outcome of a visual analytics process. They're more of the outcome of a design process. And part of the reason why I'm showing this is that some of you may have a little bit of a struggle trying to draw the division line between what design per se is about and what visual analytics is about. So let me show you some examples. So here is the prerequisite map and the major requirements map for the School of Communications here at SFU. And what it's showing there in the center is that you have to take 120 credits. In the upper right are a number of credits you need to take and what those courses should be. And on the left are a number of 40 credits that you need. Bottom left are the number of credits you need to take and what kind they are. Breadth humanities, breadth social, and so on and so forth. And in the upper left are the things that you need to take in the upper division. So this is, you know, it's reminiscent of a visual analytics display. It's showing it in a kind of a pie chart type of style, but clearly this thing has been handcrafted in order to enable, hopefully, maximum understanding on the part of communication students who may be interested in taking a communications degree. Here's SIAT's variation of that theme. This might be a little bit old now, so don't quote me if you're planning courses at the moment from this map, but this is a map of the SIAT curriculum, just focusing on the SIAT courses alone. And unlike most prerequisite maps, which go top to bottom, this one goes from bottom to top with first year, providing the substrate for your learning. The second year courses here, and we're using color in this map to indicate the concentrations and the courses associated with each concentration. So media arts in this reddish color, design in this bluish color, and interactive systems in the greenish color. And if you're wondering, you are here, right at this location, IAT814. Sorry. Okay. Here's another visualization-inspired map illustration, and this is about the progress of the previous coronavirus, SARS-1, that happened in 2001 and 2002, and this shows the progress of that coronavirus from Guangdong province in China to an individual moved from Guangdong to a hotel in Hong Kong, which is very nearby, as you might know, and stayed in that hotel. And unfortunately, in that hotel, it wasn't ideal in terms of quality, and there was a little bit of plumbing problems. And so a number of people, indicated by the letters B through K, I think, caught SARS, or the first coronavirus, from that individual via the hotel, and then traveled around the world to locations you can see. So F and G traveled to Canada. F infected 4 family members. G, had the disease, and that coronavirus from many years ago propagated itself around the world. However, the difference between our coronavirus and this one is that SARS was a little bit more deadly, and its incubation period, I believe, was shorter. And so it was a dangerous thing to get, but because of its danger, it was not. It was a little bit easier from the epidemiological point of view to combat and deal with. So what we are interested in our course is about abstraction, about taking the numbers and doing something with them in an automated manner. The things that we'd shown immediately in the previous slides, there is a significant amount of handcrafting in order to make those visual displays understandable. If I may go back a single slide, this SARS map, this thing is, the result of a number of, many man-hours of investigation, and the outcome of that investigation is summarized in this diagram. What we are not trying to do is to create visual representations of real things. We're not intending to illustrate processes. Instead, what we are trying to do is to take data about something and draw pictures on the basis derived directly from that data. So that's what we're intending to do with respect to visualization. So that concludes this subset of lecture number 1, visualization subfields. And so let's stop right there so that you can then move on to the next part.